suppose D is a region in the plane, the XY plane. So I'll sketch it here. Suppose this is a region D, and this region D is doesn't even have to be bounded, but it's at least connected. So that just means that there's a way to get from one point to another in the region. But it could be unbounded. It could be the whole plane, actually, if we wanted to. But let's just draw it like a peanut shape here. So suppose we have this region D. Then we want to define something called a probability density function on this region. And I'm going to call it a PDF, but a probability density function on this region D is a function f with the following properties. So this function f takes in points from D and it assigns to them real numbers, and it has the following properties. So it's a function such that, number one, f is continuous. So f is continuous on D. Number two, f is positive on D. So f of xy is greater than or equal to 0 for all points x comma y in D. So it's either 0 or it's positive. It's a non-negative function. And then here's the third criteria, is the one that makes it a probability density function, and that is that the integral of this function f of xy over D with respect to A with area, so the double integral over this region, this double integral is just equal to 1. Okay, so these three properties define a probability density function on the region D. And so the way this works is as follows. At any point, the probability that this, so if we have a continuous random variable, or two of them that are linked by this probability density function, the probability of any point occurring is 0. But if we, so call this point P, if we want to measure the probability that that point lives in some sub-region, some subset of D, so let's call this S. These colors are probably not a good choice here, but this region S. So the probability that any point P that's originally in D is also in S, where S is a subset of D, this is then given by the integral. So the probability that this point P is in S is given by the double integral over just S of f of xy dA. And because of the properties of the function f, that it's non-negative, that the total integral is 1, that it's continuous, then this number is less than or equal to 1. Okay, so if this integral equals 1, the probability is 1, or 100% that our point must live in S. If it's less than 1, then the probability is smaller, obviously smaller than 1, that it lives in S. Okay, and so this is a probability density function, and we can measure the probability that a point lives in any subset of D by taking a double integral. Now the other thing that we're going to want to do is, suppose we have what are in stats called continuous random variables. So this is a random variable, but it's modeled by this probability density function. Now we're not going to get into stats, so if you've taken stats you might have heard this term. If not, don't worry about it. But what we want to do now is we want to compute the expected value of this random variable with respect to this probability density function. So we're going to assume that we have this region D, a domain D. We have a probability density function which we believe is accurate for some reason. Either we've tested it or modeled it somehow. And we want to compute the expected value, the so-called expected value, or expected values, because there's two variables here of x and y. All right, and actually it turns out that the expected value of this probability density function for any random variable is just the center of mass of this domain if we think of it as a lamina. So all the work that we did for the laminar regions in the previous exercises, we can just apply to this probability density function. And one very interesting fact now is that if we think of this as a laminar region, then the mass of this region we've assumed is 1. So actually the expected values are just the moments with respect to the different axes. Okay, and so in stats we call the expected values mu. These are like means. But the expected value of x is actually the moment with respect to y. It's a little bit weird. but we're going to just call this mu sub x, and this is the double integral over the region D of x times rho. The rho, I'm thinking density here. So the rho in our case is the probability density function f. So x times f of xy dx. This is the expected value of the x variable. Same thing with y. Mu sub y, I won't even write the moment notation to avoid the confusion. This is the double integral over d of y times f of xy dA. These are both with respect to the entire area element, dA. Okay, so the expected value is a point. The expected value is a point, and it's given by mu sub x comma mu sub y. And these two, mu sub x and mu sub y, are given by these two integrals. So in the statistical notation, the x here matches the x in the integral, y matches the y. These correspond to the moments with respect to the other variable, but you know, that's just to relate the two ideas. As far as stats is concerned, we just remember these definitions, and this is what we will compute for our examples moving forward.